Alright, so in this video we're going to be talking about free fall, and I'm sure many of you are already familiar with the term, but we're going to be talking about the physics concepts of free fall. So think about this question. Which is safer to catch? A stone dropped from the top of a 2-meter pole or from the 5th floor of a building? Well, I'm sure without even knowing the physics behind it, most of you say, oh yeah, I'd rather catch something that's 2 sticks high rather than 5 floors up. And after this lesson, you should know the physics why you would prefer 2 meters instead of 5 floors. All right, so some questions to consider. Do heavier objects fall faster than lighter ones when starting from the same position? Does air resistance matter? If the free fall motion has a constant acceleration, what is this acceleration and how was it found? How do we solve problems involving free fall? All right, so we're going to go way back to when science was first getting started. So Aristotle, I'm sure many of you are familiar with him, Greek philosopher, very famous guy. He lived from 384 to 322 BC. Yes, those dates are right. It's before BC, before AD, so that's why we're counting down. So anyways, he actually wrote a book called Physics. He looked at a lot of how the natural world works with non-living and living things with motion. So he found that whenever you drop heavier bodies or heavier objects in water or some sort of dense medium, that they fall faster than the lighter ones. So from about 300 something BC all the way up until the late 16th century, it was generally believed that heavier objects always fall faster than the lighter ones. But, of course, Galileo had to one-up Aristotle. He actually figured out it's not that. He hypothesized that two objects would fall at the same rate, regardless of their mass. So the way he proved this is that he conducted an experiment. He measured the speed of falling objects by allowing metal balls to roll down the inclined plane and timing them with a water clock. So he found that the two objects, no matter what mass they were, they fell at the same rate. So who was right? Well, definitely Galileo. So the answer is because in the absence of air resistance, it is found that all bodies, regardless of its size and weight, at the same location, so the same starting point above the Earth's surface, will fall vertically with the same acceleration. And we're going to find out what that same acceleration is. All right. Another piece of evidence to prove at the same rate. So the mission Apollo 15, there was an astronaut, David Scott, and this was back in the 70s, 1971. So on this Apollo 15 mission, they traveled to the moon, and David Scott dropped a hammer and a feather at the same time. So I have a short video clip just to show you what happened. All right, here he comes on the scene. He's got the hammer on the left-hand side of the screen, the feather on the right-hand side of the screen. All right, he's getting ready to drop them. And remember, he's on the moon. Are you ready? All right, so hopefully you were paying attention as to what actually happened. So, as you saw, the hammer and the feather fell at the exact same rate. So free fall. We're talking all about free fall. It is the motion of an object under the effect of gravitational force only. So when something is in free fall, the only force that is acting on it is gravity. That is it. All right, usually whenever we're thinking about free fall, you're thinking of jumping out of an airplane, parachuting, but those few minutes before you actually open up your parachute. But really, free fall is any time there's an object falling through the air. You could drop your pencil and that is free fall. The pencil would then be in free fall. So, a very important note, free fall does not mean that the object is falling down only. I know with free fall, you're thinking that an object has to be falling downward, but in free fall, it just means that the motion is only vertical. So there's no moving left or right, no horizontal movement. It is only vertical. So that means that the object can be thrown upward, straight upward. The objects can be thrown straight downward, and it can be released from rest. So like you hold out your hand, drop a pencil, that's released from rest. So all of those examples are all free fall. So when we're talking about free fall, we're talking about only gravity acting on the object. We don't really consider air resistance because it's usually not that significant. However, one example that would show you air resistance clearly is paper. So, of course, if you drop a flat piece of paper, you have way more air resistance. As you can see in the picture, at 1 second, the ball and the flat piece of paper are there. At 2 seconds, and at 3 seconds. So as you can see, the air resistance really did affect the motion of the paper. However, whenever you take that same piece of paper and you crumple it up, you can have less air resistance. And to prove it, at the first second, there it is. Second, there they are. Third second. So of course it's still not even with the ball because there's still some air resistance, but the crumpled up piece of paper does have less air resistance. In a vacuum, both feather and apple falls at the same rate. So that is because in a vacuum there is no air. So if there's no air, then there's no air resistance. So that means that the surface area and the mass makes no difference because obviously the apple has more mass, but the feather has more surface area. Okay, so as you drop things, so imagine you're a person standing on the cliff and you drop some sort of object. At time 0, you're dropping it, so the velocity is going to be 0. But after 1 second, it's now negative 9.8 meters per second. And remember that negative sign just indicates that it's falling downward. Now, after 2 seconds, the object that we have dropped is now negative 19.6 meters per second. And then after 3 seconds, it is now negative 29.4 meters per second. Then after 4 seconds, it is negative 39.2 meters per second. So you should see the pattern, right? You should see that it's increasing by 9.8 every second. We are adding 9.8 every second that goes by after the ball has dropped. So there's a distinct pattern. It's a constant increase of 9.8 for the velocity. So because we're increasing the velocity, that means that we are seeing acceleration at a constant rate. So the change in speed is due to gravity. Hence, the acceleration in this case is called acceleration due to gravity. So for all these instances, you're always going to be using gravity as negative 9.8 meters per second squared. But sometimes we could also use negative 10 just because it's a lot easier to do some math in our head real quick by just multiplying or dividing by 10. So to find the gravity, here is our equation. You won't actually have to do this because we know gravity is always negative 9.8 on Earth. You would take the final velocity minus the initial velocity and divide that number by the time. Also, when the initial velocity is 0, so say you're dropping something, the initial velocity is 0, it's starting from rest. That means that you can find the final velocity by multiplying gravity times time. This equation is super important, and we'll be using this one the most. So to find the final velocity of a falling object, you're just going to multiply gravity times time. So let's say that you want to find the final velocity of an object that fell for 5 seconds. You would have negative 10 meters per second squared times the 5 seconds. So the final velocity would actually be negative 50 meters per second. So the final velocity of the object would be 50 meters per second down. All right, let's review our signs for position, velocity, and acceleration. So imagine that you have an object here above the origin. What would the sign be, positive or negative? Positive, right. Some number above 0, it would be a positive number. Maybe it's a positive 4. All right, let's say that now you have an object down here below the origin. The sign would now be negative, so maybe it's a negative 6. All right, let's talk about velocity now. Let's say you have an object that's in the negative position, however, it's going upward. So what would our velocity sign be? Right, it would be positive. So maybe the velocity is positive 2 meters per second. Now let's look at the opposite. So now we have an object in the positive position, but it's moving towards the negative. So what would the velocity sign be then? Negative, right. So maybe it's a negative 3 meters per second. So remember, position is based on where you are. Velocity is based on where you're going. And acceleration due to gravity is always what? Should be thinking negative 9.8 meters per second squared. So acceleration is always going to be that negative 9.8, negative g. All right, so free fall notes. So remember, for free fall, we're talking about motion that only happens in one dimension. So one dimension just means it's only happening vertically, up and down motion. That is it, no left and right. For free fall, gravity is the only factor that is causing objects to speed up, slow down, or change direction. Okay, so in this scenario, we have a person dropping an object. If you were dropping an object, it is starting from rest in your hand. So the initial velocity is 0. The final velocity is not 0. Let's say that it took 5 seconds for this ball to hit the ground. 5 seconds would be our final position. In that 5 seconds, it says that our velocity is 49 meters per second. So not 0, it's some number. If an object is thrown straight up, so he's throwing the ball straight up, so he's launching it. Because he is launching it, it has some sort of velocity. So as you can see, the velocity is positive 20 meters per second. And remember, it's positive because it's going upward in the positive direction. He's going towards the positive direction with that object. All right, so as we've already said, the initial velocity is not 0, it's some number. The final velocity would be that position at the top. This is actually the final velocity whenever we're talking about objects thrown straight up. So this is the initial position whenever he launches it. The final position is at the highest point. At this highest point, you'll see the velocity is 0. At this exact moment, the ball is slowing down to change direction. So at 0, it's at the highest point it's going to be, and then it's going to start accelerating downward as it falls back down. Okay, and you should also notice that there is a time symmetry and a speed symmetry. So assuming that the launch height and the landing position are the same, you have this symmetry. So the launch height and the landing position are the same, you see this symmetry, right? So negative 19.6, positive 19.6, negative 9.8, positive 9.8, and then 0 because this again is our final position. So there is a time symmetry. Also 0 to 1 second, 2 second, 3 second, 4. But again, this is only when the launch height and the landing position are the same. All right, and I think this is our last slide. So these are the equations that we're going to be using for free fall motion. You can feel free to write these down. So remember each variable, Vf, the final velocity, is equal to Vi, the initial velocity, minus gravity times time. So mostly we will really be using this one a lot. We may use the other two sometimes. And remember, if you were dropping an object, the initial velocity is always 0 for a dropped object because you're releasing it from rest. So if it's dropped, that means that these equations get a lot easier. So all the initial velocities would then get removed and you wouldn't even have to worry about them. All right, we will go over these equations more later whenever we do some calculations that go with them. All right, Thank you for watching. If you have any questions, leave a comment or shoot me a message. Thanks.